Hello and welcome to Lesson 7. This second lesson on heat transfer will be using the workflow and basic principles we learned last lesson to examine more complex and hence more relevant heat transfer problems. We're going to start by examining the case where the BO number is greater than 1. In other words, for situations where the temperature field in our extruded object is two-dimensional rather than one-dimensional. This is usually the case given the low thermal conductivity of polymers and the dimensions of a lot of extruded products or profiles. So, to start with, let's review the workflow we came up with last lesson, and then we'll see how to apply it to this kind of problem. So, here on the whiteboard is a recap of the workflow that we used last lesson to solve heat transfer problems. Remember, it consisted of 4 steps. The first step, really important step, draw a diagram, sit down, think about the problem and understand it. Identify the various modes of heat transfer that are likely to be present, and then try and understand if any of those are dominant. For example, you might have a convection dominant problem, or you might have an advection dominant problem, in which case it can greatly simplify the kind of heat transfer solution you're looking for. So we're looking to create a mental model. We're looking to understand what's going on. We're looking to figure out that if there is a temperature profile, what kind of profile might we expect? So, for example, if we think convection is actually a really important part of the problem and is driving the heat transfer, we know that convection is driven by a temperature difference between the object at a certain point along its length and the far field temperature. And if we're losing heat in direct proportion to that, then the object's going to cool, but that driving temperature difference is going to be reducing. And so as we move along the extradate, proportionately, we expect there to be less and less and less heat transfer. Therefore, we expect a nice curve of a temperature gradient, a reducing curve. So create that mental model. Try and foresee what the answer you're going to calculate or compute is actually going to be. And then, if they're the same, you've probably understood the problem. If they're different, you need to sit down and figure out why they're different and figure out where the understanding has gone wrong, or conversely, where the calculation method has gone wrong. So the first step is sit down, think about the problem, draw a diagram, really understand it. Don't dive into calculations or don't dive into writing computer code. The second step, we need to decide whether the problem we're solving is one-dimensional or multi-dimensional. And this is where we invoked our knowledge of non-dimensional groups and we used the BO number. And the BO number effectively looked at the competition between internal conduction and external convection. If internal conduction dominates the problem, then there's unlikely to be a temperature profile in the convection direction. Remembering that convective heat transfer is going to be lost from the surfaces, and we're going to say that is vertically up or vertically down from a horizontal surface, and that the internal temperature gradient in the material is unlikely to exist in that direction if you've got a very, very good conductor of heat. For example, a metal. It will exist along the length of the extradate or the product. If convection dominates the problem, then, well, if we've got conversely a poor conductor, well, we're probably going to be generating an internal temperature profile because as heat leaves the surface, more heat's got to replenish that surface from the interior of the material. And if we've got a poor conductor, that's actually going to be the rate limiting step in the problem. So we can invoke a non-dimensional group in step 2 to help us understand the problem yet further. Step 3 is we chose the coordinate system that best represented the problem. In simple geometries, for example, sheet extrusion or film extrusion, or maybe fibre spinning, then the coordinate system may ideally suit or identically suit the geometry, a Cartesian geometry or a cylindrical polar geometry. And then what we do is we take the energy equation in vector form, we look at each of the terms in turn and say, well, we can neglect this, we can neglect this, we can neglect this, we need to include that. That's one-dimensional, so that only changes with one of the coordinate dimensions. We can neglect this bit and we can include that bit. And so in vector form, we're simplifying the equation because we can look at the physics a lot more clearly when the equation is in vector form and not get lost in the expansion into the mathematics. And then once we've simplified in vector form, we can drop it into the coordinate system of choice. And by that point, we've probably got a very, very simple partial differential equation, or an even simpler ordinary differential equation. The final step of the process, think about your boundary conditions. What's going on? Where's the convection happening? Where are the constant temperature points? So for example, an extruded product leaving an extruder, we might know what the die temperature is. That's probably set. We've probably got convective heat loss from surfaces. Then we need to think about what's happening at the far end of our extruded product. We might make a somewhat circumspect or crude assumption that the temperature gradient falls to 0. Or the temperature gradient is controlled by a convective process. Either works. So that was our workflow. We sit down, we really think about the problem, we chew it through, we simplify it as much as we can, we figure out how non-dimensional groups can help us, the BO number for step 2, the Nusselt number as well, don't forget the Nusselt number, that allows us to evaluate the magnitude of that heat transfer coefficient, and also the Peclet number, which allows us to figure out whether advection dominates or not. So we're going to use this workflow for a very, very, very similar problem to that we looked at in the last lesson. We're going to look at extrudate problem, extrudate cooling. We're going to look at, instead of a thin film cooling, an extruded slab cooling, because what I want to do is to give an example of two-dimensional heat transfer. So let's go through this workflow. Let's start with step 1. Let's draw our diagram. So here on the whiteboard is my extruder, simple single screw extruder, sheet die, big thick extruded planar product with convective heat flow through a quench, an air quench, and then we're going to some rollers at the far end of the process to haul the product off. All right, so let's focus on a section of our extrudate and let's figure out where the heat transfer is going on. So there in the red box is a cartoon of my extrudate, and I've got a quenching airflow. So convective heat loss is likely to be the way that heat leaves the extrudate. Fine. Okay, so that's the convective heat loss there in blue arrows. I've got a moving product. I'm extruding product and I'm hauling it off with rollers, probably at a different speed, probably because I'm drawing the product down a bit. So I'm going to have advection. So there with the pink arrows, they represent the energy advecting into and out of that red control volume as a result of extrudate motion. I need to think about conduction as well. So I can have conduction in either or all of the coordinate directions. And so I can have conduction heat transfer along the extrudate in the extrusion direction. And depending on the relative temperatures, we can have heat flow from left to right or right to left, depending where the temperature gradients lie. I can also have heat flow up and down. So I've got a thick product, I've got a poor conductor of heat, I'm likely to have a temperature gradient in the convection direction within the product this time. And so we can sit down, we can draw our diagram, we can understand what's going on in terms of the various processes of heat transfer. On my diagram, I'm also going to think about boundary conditions. So my extrudate leaves a die, the die is at a set point temperature. I can assume that's probably well described by a constant temperature boundary condition. At the far end of the extruder near the rollers, I've got that question as to, well, what exactly is going on here? We may need to make a bit of an assumption. I'm going to assume that for the time being that it's a 0 gradient boundary condition. But we're going to be solving this problem numerically, and so that gives us more flexibility as to how we can describe that boundary later on. I've also got that quenching airflow, so I've got convection happening at that top and bottom surface, and I will be describing that using a heat transfer coefficient. All right, so that is my diagram of the heat transfer process. These are the physical processes that are going on, and so I've got convective heat loss from the film surface, or the sheet surface. I've got advection due to film motion, and I've got conduction going on within the material. So I've neglected radiative heat transfer again. We did a little bit on radiative heat transfer in the final part of the last lesson, and I'm going to assume that you're able to include that as an effect if required. But for the time being, and for purposes of illustrating this example, I'm going to neglect it. All right, so step 2. Let's see whether we've got a one-dimensional or a two-dimensional temperature field. In order to do that, we need to specify the problem in a little more detail. So let's assume that we're extruding a thick polypropylene slab. The thermal conductivity of polypropylene is about 0.172 watt per meter per Kelvin. Density is 910 kilos per cubic meter. Specific heat capacity is 2,140 joules per kilo Kelvin. The extrudate thickness I'm going to deal with in this problem is 100 millimeters. Note that so far, up until that point, the setup is identical to one of the problems we solved in the last lesson. The thing that's different is at last lesson, our film was only 5 millimeters thick. Now we're 100 millimeters thick. Okay. I'm also going to assume that I'm looking at a length for cooling of about 0.5 meter. All right. So let's look at two key heat transfer cases. The first case is going to be very analogous to last time. We're going to have a static extrudate with convection at the surface. So this, if you like, is when the extrusion line has been shut down. There is still product coming out of the die, but it's not moving, and that product is still cooling by natural convection. And we're going to look at the steady state temperature profile because the die is still hot. And so there is still the opportunity for heat to be conducted along the length of the extrudate. And we're at a steady state where that conduction of heat in is equal to the loss of heat out by convection. I'm going to assume a value of my heat transfer coefficient of 50 watt per meter squared Kelvin, and we now know the various means by which we can obtain heat transfer coefficients by Nusselt number correlations. So that's my first case, static extrudate. The machinery is effectively shut down but at temperature. And the second case I'm going to look is an incredibly slow moving extrudate, 1/3 of a millimeter per second. I've chosen this frankly ludicrously low rate to illustrate a point later on in this lesson. And so we can imagine maybe we're just getting a creeping motion of the extrudate away from the extruder. Maybe we're just starting a line up, or we're running the line incredibly slowly just to see what's going on. Okay, so let's figure out a BO number. My BO number, as we know, is that balance between internal conduction and external convection, and gives us a steer on which of those two factors dominate. Substituting in the values for the BO number for this particular problem, we find that it is greater than 1. It's about 14.5. So we have a two-dimensional temperature field. We have a temperature field along the length of the product. We also have a temperature field in the convection direction, that is to say, across the thickness of the product. So we need to calculate the temperature field for the entire extrudate now. We can't just assume that it's a simple cooling profile in the length. We're going to do this numerically. We could do this analytically. There are analytical methods by which you can solve this kind of problem, but this is a practical applied course rather than a purely mathematically focused based course. So we're going to revert to numerics because that gives us a rapid means of obtaining the answer, and also gives us a lot more flexibility in how we specify the problem. We could, for example, change the heat transfer coefficient on the bottom and top faces of the film. We could put an additional heat transfer coefficient at the end of the film, and that will change the form of the answer, and that would be incredibly difficult to do using analytical methods. So with this in mind, we're still going to stop and pause, and we're going to see if we can embellish our mental model a little bit more. So now that we've decided our temperature field is two-dimensional, let's think more about our mental model. We know that it is likely that we're going to have a temperature gradient along the length of the extrudate, and we know that's probably going to be sort of an exponential type decay. We saw that last time. Now we need to think about what's going on in the middle of the product. We're losing heat from the edges. That's cool. The edges are cooling quickly. It takes time for the heat in the middle to get to the edge, and so I'd expect a sort of symmetric gradient across the thickness of the film or sheet as well. And those two different gradients will be what I'm expecting to see in the numerical solution. If I don't, I'm going to ask very, very strongly why. All right, let's go on to step 3. We've understood the problem. We've got our mental model. We've identified it's two-dimensional. Let's revert to the energy equation and see what terms are 0 and non-zero. Now, we're going to write the energy equation to start with for the bulk of the material, away from the boundaries. We want to see what's going on inside the material first, and then we'll treat the boundaries by establishing the correct boundary conditions. So let's think about the bulk of the material, far from the boundaries. There on the board is the energy equation written in vector form. So let's go through it term by term. There's no heat sources, no volumetric heat sources. I haven't got any crystallization going on. I haven't got any phase changes going on. I'm assuming that there's no radiative heat gain or loss that affects the bulk of the material. Furthermore, I'm neglecting factors such as viscous dissipation. So no heat sources. Let's look at those heat transfer terms that are wrapped up with heat fluxes. I'm neglecting radiation. I'm going to include convection, but only as a boundary condition, because remember we're looking at this equation in the bulk of the material at the moment. I'm going to include conduction heat transfer because that is happening within the bulk of the material, and it is happening in both the x direction and the y direction. Let's look at the terms on the right-hand side of this equation. I'm assuming we've got a steady state problem. Whatever temperature gradient has been established is a steady pattern. It's a steady temperature gradient. We'll look at transient problems in the next part of this lesson. That final term, the advective heat transfer, I know is 0 in case 1 because the film is static, but non-zero in case 2 because it is moving with a certain prescribed velocity. Okay, so those are the 0 and non-zero terms in my energy transport equation. Let's now drop those into the coordinate system we've chosen and write the simplified differential equation that describes the problem we're attempting to solve. And we can see that we're just left with two terms. We're left with a balance in the bulk of the material of conduction versus advection. Our conduction heat transfer is two-dimensional, and that is why we've got those two second derivatives on the left-hand side, d2t by dx squared plus d2t by dy squared. On the right-hand side, we've just got the non-zero component of that dot product of the velocity vector with the temperature gradient vector. Okay, so we need to solve this partial differential equation somehow. We're going to do it numerically, as I've said. We could do it analytically, but we're not going to. So let's figure out what boundary conditions are required in order to solve this equation. So I'm going to solve this equation in one fell swoop. I'm going to set the equation up numerically to include advection and conduction together. But for the first case, I'm simply going to set the velocity parameter to 0 to turn off advection. And then when I want to look at advection, I'll simply turn it back on again by setting a non-zero value for Vx. Okay, so in terms of the boundary conditions, at point 1, where the sheet is leaving the die, we're going to assume that there's a constant temperature, that is the die temperature. That doesn't seem to be a wildly unrealistic assumption to make. That's probably pretty good. Okay, so to x equals 0, t equals td for all of y. Remember, we're having to specify y and x now. For boundary 2, the top part of the film, we're going to say that along the entire length of the film, so for all x, we're going to have convective heat transfer driven by the temperature difference, which is going to be a function of x, and our heat transfer coefficient h. Okay, let's have a look at the end of the die. This is the boundary condition that we can debate. I'm going to assume, correctly or incorrectly, that there's going to be negligible convective heat flux in the extrusion direction. So I'm going to assume that there's no gradient here in the x direction, so dt by dx equals to 0. The reason I'm choosing it for this particular problem still is because it gives me a direct analogy to an analytical solution that I can use to check my numerics. And once I'm happy with my numerical check, I can then change that boundary condition to something that might be a little more realistic, and we'll see that a little later on in this lesson. Let's think about the fourth boundary condition, the lower surface. Again, I'm going to assume there's convective heat transfer going on along the entire length, so my convection heat transfer is going to be valid for all of x. Furthermore, I'm going to assume that the heat transfer coefficient h is the same on the bottom surface that it is on the top surface. It's not likely to be the same because there's going to be a mixture of buoyancy-driven convection and forced convection. But again, I'm setting it the same to start with because it gives me direct analogy to an analytical solution in 1D that I can use to check the answer I'm getting. Okay, so there are my 4 boundary conditions on the left, right, upper and lower surfaces. So let's set the problem up. I'm going to use Mathematica as my package of choice to solve the problem numerically. And again, I've explained why I've chosen Mathematica in previous lessons, and it's predominantly due to the fact that you don't have to have any detailed knowledge of numerical analysis in order to get some reasonable answers out of it. So the first thing I'm going to do is to set a load of parameters. So if we look, this is a list of variables. I've got K as my thermal conductivity, 0.172 watt per meter per Kelvin. Rho as my density, 910 kilos per cubic meter. Cp as my specific heat capacity of 2,140 joules per kilo Kelvin. V there is the advection velocity of the film, and I'm setting that initially to 0, so V there is Vx in the equation that I've written down. L is my extradate length, B is my extradate thickness, W is my extradate width, which hasn't featured in the analysis so far, apart from the fact we need an area to volume ratio for the heat transfer. So that's why I've got W there. It allows me to work out my volumetric surface area. Tinf, right, this is my far field temperature, 298 Kelvin, roughly 25 degrees C. Td is my dye temperature, which I'm assuming is 550 Kelvin. And then I've got my 2 parameters that are derived from these basic specifications, which is my area, my surface area, and my volume. Okay, so having defined the parameters for the problem, we need to find the geometry of the problem. And what one can do in Mathematica is say, right, I've got a geometric shape. I've got a polygon, I've got a rectangle of these particular dimensions that represents the heat transfer domain or the partial differential equation domain that I wish to solve on. And I'm going to use a rectangle here. So let me just illustrate what this is saying. Capital Omega is just a designator of my geometry, and the rectangle is defined from the bottom left corner to the top right corner. So it's 0, 0 at the origin at the bottom left, and the length and the breadth in terms of xy coordinates at the top right corner. So that's what that definition means there. The next thing I'm going to do is to specify the equation that I'm solving. Right, so let's look at this in a little bit of detail. And let's look also how we treat the boundary conditions. Let's deal with the equation to start with. So the blue terms and the pink terms are simply the rearranged version of the energy transport equation that we had simplified to be pertinent to our problem. The blue terms are the advective terms, and we can see in the Mathematica script there, we've got very strong correspondence with what is written in the equation lower down on the whiteboard. If we'll examine how we're writing the derivative, capital D is Mathematica language for take a derivative. And when you're taking a derivative, you need to tell Mathematica what it is you're taking a derivative of, the temperature field in x and y, T, x, y, and which direction we're taking that derivative, x. Okay, so big D square bracket, T square brackets, x comma y comma x means take the derivative of the temperature field, which is 2-dimensional in x and y, with respect to x. So it's partial dt by partial dx. The pink terms are the conduction terms. And again, we can see that K, the thermal conductivity features. And let's again look at our differential operators. And it's very similar to what we just looked at, except now we have 2 x's following the field that we're taking the derivative of. And that just means, well, we're taking the differential in x and then in x again, so it's the second differential with respect to x, d2t by dx squared, written in partial form. And the same again for y. So the pale blue and the pink terms are the equation that we derived for the bulk of the material. Now, when we're setting this in Mathematica, we're saying, well, okay, in the bulk of the material that's going to be 0, but if we're taking boundaries into account, we also need to represent the heat loss or gain those boundaries correspond to. And that's what the sum of convective terms, sum q convect, equals there on the right-hand side. And we can see we've got our 3 convective boundary conditions included. So let's look at those. Boundary 2, Q equals HT minus T infinity. And if we look at the blue script, a Neumann value basically means it's a flux value. H is my heat transfer coefficient times T of xy minus T inf. That's my temperature driving force, T minus T infinity. And then in following the comma, we've got the geometric part of the domain that corresponds to. So y equals b, so that is the top surface, from x is 0 to L. So that's the entire length of the top surface. So we could segment that top surface with different heat transfer coefficients if we wanted to. All right, we've got exactly the same thing going on with the gold statement. That is still my heat transfer by natural convection on the lower surface. We know it's a lower surface because y equals 0, and again x equals 0 to L. And of course we could have a different h value there if we really wanted to. Let's look at the green boundary condition. That is the convection at the tip. And note that I've written it 0 times T of xy minus T inf. And that is effectively saying the temperature gradient there is 0. Again, I could make that non-zero if I wanted to, but I'm leaving it at 0 for now. So that sets all the flux-based boundary conditions. There's just one left we need to specify, and we need to do that separately of the definition of the energy equation. What we're saying here is that for a fixed temperature value, rather than the flux, we need to say that specifically the temperature at x equals 0, but for all of y, T of 0 and y, is my dye temperature, Td. So that sets the equation and the temperature boundary conditions. So the next step is to solve it. The Mathematica command for solving that is nd solve value. And let's look at the structure and the syntax of that statement. In curly braces to start with, we specify the equation that we're solving with the boundary conditions. Then we specify the parameter that we're solving for, the temperature as a function of x and a function of y. And then we're specifying the geometric region over which x and y exist. So curly brackets x and y belong to my domain capital omega, which is my rectangle. So that's all that that's saying. And so that will compute a numerical solution. And then we need to visualize it. So I'm going to contour plot the solution. And I've got some specifications there that I want 30 contours and I want a temperature map type representation. And I don't want any cropping of the data. All right, let's see what that gives us. So my contour plot of temperature within an extradate, ta-da, looks like this. And I'm going to compare it to my mental model. I was expecting a gradient along the length, which I have. I was expecting a gradient across the thickness, which I have. The key standout feature here is that the bulk of the material hasn't really got any temperature gradients at long length. And that again corresponds with my mental model because we've got a poor conductor of heat. If all that's happening is I've got a long slab of polypropylene with one end held hot, I'm not expecting, due to the poor thermal conductivity of the polymer, that heat to travel very far. And that is what that solution seems to suggest. However, it's all very pretty. Can we actually trust this? So we need to validate numerics every time we write a numerical code. So I want to validate this without changing the code because I want to validate the code that I've written. So I want to change the parameters such that they represent a problem that I can get an analytical solution to. So the simplest way of doing this is to say, well, if I change the thermal conductivity, I'm going to reduce my BO number and I'm going to reduce the problem from being two-dimensional down to one-dimensional. So arbitrarily, I'm going to multiply my thermal conductivity by a factor of 100. No, a factor of 1,000. So I'm going to go and choose my thermal conductivity as being 1,720 watt per meter squared Kelvin, which gives me an incredibly tiny BO number. Fine. So with that very small BO number, I would expect a 1D problem. I'm then going to plot the temperature profile as a function of length at different sections of thickness of the extradate. They should all be the same. And then I'm going to compare those answers to the analytical solution for one-dimensional heat transfer that we looked at in last lesson. So the Mathematica code required to do that is on the board now. The first thing, I'm just defining a different solution for this because I've already got my nice solution for the 2D field. So I'm going to ND solve value again, so numerically solve the differential equations, the same differential equations for temperature as a function of x and y on the same domain. The only thing that's changed here is how I've written t. Because I want a line graph, I'm just writing t rather than t square brackets x comma y. I'm also going to define a function that is my analytical solution, which involves those hyperbolic trigonometric functions that we derived last time. If you can't remember the form of the solution, go and review last lesson's derivation of this. And then I'm going to plot both the analytical solution and various temperature sections from the numerical solution. And if we look at the detail here, I've got 4 plots going on. I've got an answer in the core of the material at b/2 and the upper and lower surface at b and at 0. And the numerical solutions are going to be the purple, blue and red lines. The analytical solution is going to be the grey line. So let's have a look at this line graph and see what it looks like. The corresponding temperature field is there on the board, and my line graph looks like so. I was going to label up the different parts of this as the middle bit, the upper bit, the lower bit, and the analytical, but there's 4 solutions there and they all overlay. So the analytical solution and the numerical solutions are the same. Our numerics are right, or at least our numerics correspond identically to the analytical solution for the one-dimensional problem. So that gives us pretty good confidence that when we put the thermal conductivity back to that for polypropylene, and we get that very intense temperature field near the dye and a very isothermal remainder of extradate, that's probably what's going on. Now, for that particular solution, we'd just turned advection off. Now we can turn advection on. We've validated the solution. We are confident our numerics are written pretty correctly. So let's have a look what happens if we start to move this extradate at 0.3 millimeters per second. Well, there we have on the board the contour plot of temperature. Our very cold extradate has now become a very hot extradate, almost uniformly along its length, even at this tiny speed. Can we justify this? Well, what's the Peclet number? If we work out the Peclet number for this very, very small advective heat transfer, we find it's 170. It's a lot greater than 1. So it is an advection dominant problem. And remember, we looked at advection dominant problems last lesson as well, and they effectively became isothermal. And that is what we can see happening here. For negligibly small extradate velocity, we have a temperature profile that is tending towards isothermal. If we went even at a millimeter per second, let alone 5 millimeters per second or sort of 30 millimeters per second, we would probably see a totally isothermal extradate. So I've only chosen 0.3 millimeters per second because I can get a temperature profile there that looks interesting rather than just uniformly the same color. And so if we compare that to the static case, we can see that even a tiny bit of extradate motion has a massive effect on the temperature gradient. Okay, let's recap a few key points. So we've used exactly the same heat transfer workflow that we used last lesson to use this lesson for a two-dimensional problem. We've used Mathematica this time to obtain a numerical solution to the equations that we derived using that workflow. We've validated the solution by manipulating the thermal conductivity such that we obtained a low BO number so we can compare to an existing analytical result. And we also saw that if advection was present, the surface cooling had very little effect at all. And a tiny, tiny, tiny extradate motion, we've had a very, very marked change in temperature profile.